Hello, my name is Aleksandar Haber, and this is the first lecture in a series of lectures on control systems and control theory. In this lecture, we provide an introduction to Statespace models and explain how to simulate linear ordinary differential equations or ODEs using the Python programming language. Statespace modeling and numerical simulations that will be shown in this video are demonstrated using an example of a mass and a spring system. So why do we start with the simulation of ordinary differential equations while all other control theory books and other lectures usually start with Laplace transformation or simple description of dynamical systems? Well, the reason is that by learning how to simulate an ordinary differential equation, we will naturally arrive at a state space description of a dynamical systems. And state space description is a very important concept for understanding control systems. Another question is, why do we start with mass and spring systems? Well, mass and spring systems are widely used to model the dynamics of actuators and other electromechanical devices. So, a basic sketch of a mass and spring system is given in figure 1 over here. So, we have an object of mass m that is attached to a spring and to a damper. And we have an external force F acting on the system. So let us assume that the force F is not acting on the system. And let us assume that the object is at certain distance, certain initial distance from its equilibrium point. Let's say it's over here. And the question is, what will happen if we release the object? Well, the object, of course, will oscillate. And the oscillations will have the following form. T is time and d is a distance. So the oscillations will have the following form. They will be damped. And after some time, the object will approach very close to its equilibrium point. Now, the question is, what will happen if from certain initial conditions, let's say from certain initial displacement from the equilibrium point, we apply a force F, let's say a constant force F. How the response of the system will look like? Well, if we go back to our graphs, if this is initial point, and we apply a constant force, and we keep this constant force, the oscillations will have the following form. So, if the constant force is acting on the system after some time will settle around another steady state point. Now, the purpose of simulating the system is basically obtaining these time responses. So our goal is for a given force and for a given initial condition to find how the, let's say, displacement, and not only displacement, also the velocity of the system will behave. And that's the main purpose of simulating the system. We want to predict for initial values and for a given input, which in our case is the force, how the dynamics of the system will behave. So let us start with system modeling. One of the first lessons that mechanical engineers learn in the dynamics class or in the basic physics class is how to model such a system. Basically, the first step is to derive a free body diagram of such a system. So what is a free body diagram? In layman terms, a free body diagram is basically a diagram obtained by replacing the actions of all the external bodies that act on a system by corresponding forces. And in our case, free body diagram has the following form given in figure 2. So we can replace the action of a spring on the body by a spring force, and we can replace the action of a damper on the body by a damper force. Of course, we have the force F. Now, we will look at the system behavior with respect to its equilibrium point. So if, let's say, the force F is not acting, the system will settle at its equilibrium point, or approximately will settle in its equilibrium point, and this is the point. And we will observe the dynamics with respect to the equilibrium point, and the displacements from the equilibrium point will be denoted by the W variable. Now, the spring force is proportional to the displacement W, and the proportionality constant is Ks. So the physical explanation of this equation is that the spring force is proportional to the spring displacement, and the minus sign comes from the fact that if the spring is extended, then the spring will try to return to its neutral position. Now, the damping force is proportional to the velocity, and the proportionality constant is Kd. The minus sign originates from the fact that basically the damping force, or the force inside of the damper, is always always act in opposite direction to the direction of motion, and the direction of motion is basically determined by the first derivative of the displacement, which is the velocity. The next step, of course, is to write the second Newton's law. So mass times the vector of acceleration equals the sum of all the forces acting on the body. In this case, we can approximate the body as a material point, since we are not considering a rigid body motion in 3 dimensions. By projecting the equation 3 onto the w-axis, we obtain the equation 4, which basically tells us in 1 dimension how the dynamics of the system behave. Now, by substituting the damper and spring forces and manipulating this equation a bit, we obtain the equation 5. So the equation 5 is a basic equation describing the system dynamics. The force F can be seen as an input, and the right hand side variable W and its derivatives are basically variables that are influenced by the force. Now, the next question is, what is the solution of the equation 5? So, the general form of the solution of the equation 5 is the equation 6. So basically the solution is a function that describes how our displacement W from the equilibrium point depends on the initial displacement, initial velocity, and the applied force F. And the equation 6 is an analytic form of the solution. Since the equation 5 is a linear ordinary differential equation with constant coefficients, we are able to find a closed form solution given by equation 6. However, this is not the purpose of this video. The purpose is basically to find a numerical solution of the equation 5. And by basically deriving this numerical solution, we will arrive at the concept of state space models, which is a very important concept for understanding control systems. To define a state space model, we first need to introduce state space variables or state variables. In our case, the state variables are denoted by x1 and x2, and we define them by equation 7. So the first state variable equals the displacement, and the second state variable equals to the velocity. Now, taking the derivative of the first equation in equation 7, we obtain that the first derivative of the first state variable equals the second state variable. Now, the first derivative of the second state variable from equation 7 is basically the second derivative of the displacement variable. That is the acceleration. Now, from the equation 5, we can express the acceleration as a function of velocity and position and the force F. And using this equation, the equation 7 and the first equation in equation 8, we can express the first derivative of the second state variable as a function of the second state variable, first state variable, and the force F. The two equations in 8 can be written in the vector form. If we group the state variable x1 and x2 in the vector x, we can obtain the vector equation 9. Now, the vector equation 9 can be written compactly as the equation 10, and the equation 10 is basically our state space equation. This equation is basically relating the first derivative of the state vector x with the state vector and the control input. And the implications of this equation is basically that the second order ordinary differential equation can be written as a system of two first order differential equations. And this applies also to the case of the nth order ordinary differential equation. So an nth order ordinary differential equation can be written as a system of n first order differential equations. With the state equation, basically, we usually associate an output equation. So what is an output equation? An output equation is basically an equation that maps the state vector into the system output. So what is the system output? The system output is usually something or a variable or a combination or a function of variable that is usually observed or measured. In our case, we are assuming that we are actually measuring the displacement. We can measure displacement using various types of sensors. Now, the equation 10 and equation 11 can be written as the equation 12, and this is basically our state space model with the output equation. Now, the main question is, how do we solve the equation 12? So how can we solve it using a numerical method? The first thing that should come to our mind is to use basically a forward Euler method. Forward Euler method approximates the first derivative using first order finite differences, where in the equation 13, h is the discretization time constant. It is usually a very small real number. K denotes a discrete time instant, so basically we are dividing a time axis into discrete time instants. Let's say this is discrete time instant K, and the time length between two discrete time instants is basically equal to h. So the time between k minus 1 and k minus 2 is h. By substituting the equation 13 into the state equation, we obtain the equations actually 14, and the state equation in 14 can be written as 15. Now, from 15 we see that if we know the initial condition x0, that is the state at the initial time t0, and if we know the input sequence, that is the force at certain time instants, then by simply propagating the equation 15, we can obtain the state sequences at the time instant x1, x2, etc. Now, how do we propagate the equation 15? Well, this is very simple. So we can write for x1 equals a df x0 plus b df u0. Now, knowing x0 and u0, we can determine x1. Similarly, x2 equals, again, ADF, now it's times x1 plus BDF times u1. So we can recursively compute the state sequences x1, x2, etc. This recursive propagation can be implemented using a for or a while loop. Now, there is a problem with the forward Euler method. It is very well known that the forward Euler method is numerically unstable. That is, for modest size discretization time constants h, the state vector, the simulate state vector might diverge from its true behavior. So we can represent this graphically. If, let's say, this is a true system behavior, let's say the displacement behaves like this. If h is not selected to be a very small number, the simulated trajectory will diverge and it will go to infinity and the whole method will explode. Now, to avoid this problem, it is preferable to discretize the system using the backward Euler method. So the backward Euler method discretizes the state sequence as follows. So instead of using forward finite differences, we use backward finite differences. And by substituting the equation 16 into the Statespace model, into the state equation, we obtain the equation 17. And from equation 17, by inverting the matrix I minus h times A, we can obtain the equation 18. And the equation 18 is the discretized backward Euler state space model. Now, this model is known to be much more numerically robust than the forward Euler method, and we will use this method in our simulations. So let us now explain the code for simulating the system. We are using the Python programming language. So the code lines 6 until 8 are used to define A, B, and C matrices. We are assuming an arbitrary mass spring system. The code line 10 is used to define an initial condition. Code line 13 is used to define the total number of time steps for simulating the system. Code line 14 is used to define a discretization time constant h. And code line 18 is used to define an input sequence. So in our case, the input sequence is nothing less than a step function. So we assume that the force behaves in time as just a step function, constant function, or heaviside function. And the corresponding response of the system is called the step response in the system, and it will have, as we have described, we have explained before, the form given on this figure. Now, the code lines 30 until 49 are used to define a function for simulating the system. It's basically a for loop where we propagate the discretized state equation. And the system response will have the form given on figure 3. From certain random initial condition, the displacement vector will oscillate, and it will approach a new steady state point. This was our first lecture on control systems. And in this lecture, we have basically explained how to simulate a dynamical system using a stable backward Euler method. In deriving the discretized version of the system, we have arrived at the Statespace model of the system. And this Statespace model of the system, as you will see in our future videos, it's very important for designing controllers and for understanding the dynamics of the system. Thank you for your attention.